Is everything good? Yep. So for the last 30 minutes, I would like to talk the other side of the spectrum, like guidance and control, and how AI has been influencing or research to push the state of the art, and then to some extent to address something that is unaddressed throughout this coursework. So I would like to start from some motivating scenarios and then some reviews of 279D, which is, I think you guys already learned a lot of stuff, and then learn mostly works almost perfectly. And also I would like to revisit some non-convex trajectory optimization that Professor D'Amico followed a little bit in the class. And then third, I would like to focus on some recent development of AI-driven trajectory generation called ART, Autonomous Rendezvous Transformer. And then I would like to show some demo and how it works. Okay, so to begin with, so is there anybody who's doing docking in 279D scenario? You are doing, okay, and you are doing. How did you guys formulate the trajectory or guidance law? You add some analytical solution to origin 000, or how did you solve the problem? Zero. Okay, perfect. To zero. Okay, I think that's most sort of straightforward way to do it, right? And think about a scenario where you want to have that type of mission. Let's say you want to remove the debris, which is really unknown. You first get there, you're inserted into orbit, and then what you usually do is you raise the delta A, delta semi major axis, to the point where you can start delta lambda drifting just slightly, so that you can just keep that EI separation, and then get loosely approach to the target, and then where you get into a final target where your delta lambda is squashed to zero, and then have some circumnavigation around there, having EI separation obviously, and then maybe we inspect and then figure out, oh, this is maybe upper stage, have this type of dimension, maybe we can dock here, there, out there, and then we're gonna dock. Right, sounds pretty easy, right? But in reality, think about you're just directly going towards 000. You're gonna absolutely crash to this rocket, right? So that's really not desirable. Even though you're at the end, your fragments of a spacecraft are in ROE 000. That's not what you want. And the question is how to approach this docking phase is something it's not specifically addressed in AA279D. Namely, we discussed how to get from maybe 100 kilometers of separation to maybe 2 meters, 20 meters or something, but we really didn't address okay, how we get the final approach. That's one motivating example of what we're going to talk. Also, there's some always constraints that we need to satisfy. For example, if you're docking, maybe that's super optimal, maybe almost no energy, but if your star tracker is looking at the sun, then all of a sudden that star tracker doesn't work, and then you're in the trouble of navigation. Or maybe there's some approach corridor, as you can see, there's a cone attached to the docking port where you want to get into this cone while you're approaching to the final phase. This is very much common constraint that we need to deal with. So this is not really obvious doing some numerical solver or analytical solution we have. Another example, there might be not enough time to get to the docking target that we discussed. I think for most scenario that we are dealing with, we have a relatively long time period to get from point A to point B. For example, 5 orbits, 10 orbits, 15 orbits. In most crewed space mission, for example, you want to send Dragon to ISS, we really don't want to wait for 15 hours or 15 orbits or maybe 24 hours. What we instead want to do is relatively go there quickly. And to do that, you need to leverage the fact that you can use the delta lambda drift using relatively big delta A, delta semi major axis, so that you can get there like this. Maybe you want to burn a little bit and then raise your altitude and then burn again and burn again. That is most of the kind of practical way to dock crewed space station as of now. For example, Crew Dragon or whatsoever. And the question is, okay, there's no EI separation here. Obviously, right? And then we still want to maintain this safety. And what we do is to think of the natural drift of these trajectories where you try to insert the maneuver relatively big, maybe it could be meters per sec. And then assume the scenario where these burns are missed. We call it some contingency. And then these trajectory starts drifting like this. And it is critical if these drift trajectory intersect with space station. like obviously, right? Like, like sometime when you like have a broken like spacecraft and it starts drifting and it hit the space station, and that's pretty dangerous. So we would like to have what is called passive safety. This is like fortunately achieved by careful design of EI separation when you have like delta A equals 0. But for other scenario like this, you might want to like ensure some like many like state exclusion constraint out there. And then another scenario is like, okay, let's just start drifting. Okay, that is not fine, but fortunately we recovered, great. But you're now at the like the yellow diamond, which is completely different from like your previous state. Okay, what are we gonna do? Let's say we assume like we still want to get there. Like your original guidance trajectory doesn't really work, right? And we still want to get to the docking port. How do we do that? Is like another big problem. Another issue is like, okay, there is like some uncertainty. We talk about contingency, and then there's like a very clean split like that we need to make in terms of contingency and uncertainty. Contingency is namely more like event-based accident. Your burn is missed or something like that. Uncertainty is coming from more like the fact you have a navigation uncertainty. Even actuation is properly done, your actuation might have a noise. There is like a model acceleration, and then these two comes into together, and then like these actually solving these like optimal trajectories is like very hard. Okay, so let's look back to like a little bit of like a recap of like 279D. We went over from closed form solution, starting from Professor D'Amico's PhD thesis, going to Michelle Chernik's PhD, that is like more generalizable to multi-rev scenario. They are fast and analytical. I hope like most of you or some of you have coded up and enjoyed the benefit of it. I personally enjoyed it a lot, actually. But these are very case specific, and also like there are no like consideration of constraints or so on. And there are some like solution we didn't really touch a lot, but there are a numerical solver that uses like indirect method, or Matthew had a lecture about reachable set theory, and which is also really clean, and then having some like guaranteed optimality using Pontryagin maximum principle. But still having like a nice constraint formulations are very, very hard. And then like you always need to start with like a special case of the problem. We also did a Lyapunov controller as a continuous control. These are also like having a very nice like theoretical guarantee of stability. And I think like Steindorf included multiple constraints. However, still like tuning is required to like have a nice performance. And also their performance is like fundamentally suboptimal because of the price we need to pay for stability and whatsoever. And constraint inclusion is like still pretty hard. Maybe you tried it, but like some numerical issues are always there, and then like it's really not robust at this point. And the final topic we covered is like optimization-based method. For example, sequential convex programming, or ideally convex programming. This is very general. Local optimality is like guaranteed if the problem is solved properly. And what is very appealing to us is like the constraint handling is very easy. However, for example, if the problem is non-convex, the convergence is not guaranteed, or time discretization is needed. But let's see. What if we have a real-time solver for constraint trajectory optimization? Doesn't sound pretty appealing to load on your spacecraft. It is kind of is, and it's actually pretty hard to do this because like most of these constraints I introduced is like non-convex. So real-time solver for non-convex trajectory optimization is like what we want to have. Okay, so now we go into like a recap of like sequential convex programming and non-convex optimization. So this is like what we want to solve as a non-convex trajectory optimization. Might seem a little bit scary, but don't scare too much because like it's really simple. The first line is like the minimization of objective function. Like it's kind of some of it. And then the second line is like the dynamics. Could be nonlinear, whatever. Function f describes like the state transition from like tk to tk plus 1. And those like state and constraint are, or they needs to be within some like admissible variable set. That is like kind of like living within like the admissible state and then admissible control. Sometimes they're coupled. So these are very general non-convex constraints that we need to deal with. And then of course, most of the time we want to get a certain point, the terminal state, and then like we know like where we were at, roughly speaking. And the way to solve this is like sequential convex programming, just like one way to solve this. And Professor D'Amico mentioned this already a couple of weeks ago, but this is like basically repeating the cycle of like convexify the problem, which means like you basically linearize your constraints and solve, basically you relinearize the dynamics, and then you linearize the non-convex constraints that I mentioned. And then if it's not converged, then we solve like a convex optimization. And we repeat until these like solution converges over and over and over. And the good part of doing this in ROE, that is understated in my opinion, is we have a very nice ROE STM, which is like very accurate compared to other field. For example, if you want to go to like Moon and you want to linearize the dynamics around like three-body problem, that is far more nonlinear. And then like actually SCP really struggles like figuring out how to like converge that solution. Compared to that, even though ROE STM is not exact, but usually really accurate to like deploy on board, because like we have been developing some like various perturbation, including drag, SRP, J2, whatsoever. Okay. The sad thing is like we still need to convexify the non-convex constraint. But at the end, we have a nice convex problem that we can solve over and over and over. But one thing I didn't mention here, one thing I would like to mention this. So like recently, there is some like progress in like SCP algorithm itself. And then some algorithm, for example, Gusto from Professor Marco Pavone's lab, and also like SCVX star, they have like a guaranteed convergence to the local minimum to some specific problem. At least that's what they argue. Yeah. There are some like controlled discussion going on, but most cases it really works. And so that is like done by like auto-tuning the trust region, or like they are sometimes like changing the weights or whatsoever. And it's very, very, very important to like stick with like the best SCP you can do before we go on, if that makes sense. If you set up the problem, your SCP problem like improperly, like first of all, you will not get like any benefit for the remaining time period of like the discussion. Anyways, so the part I didn't talk about is like initialization. What is like the general initialization scheme for the trajectory optimization? Many robotics people take, you're here, we want to go there, draw a straight line, and then start. And that is not really the best we can do. And in fact, think of like, this is like a solution landscape of like a problem you want to solve. On the left, there are like two basins you can see, but I mean, it looks still sort of tractable, where I mean, you see both subjectives are roughly on the same page, and then like you can start, and then like maybe like it looks relatively okay to converge your algorithm if you're using like gradient-based thing. However, the issue is like, if you have like the right side of like solutionscape, there's almost no chance you're going to get a global optimality. So the question here, or the main idea here, is like, can we learn where to start? And this comes into the emerging paradigm we are facing now in the last like few years. It's called learning-based warm starting. And the idea is like train the model so that they can predict a warm start or initial guess of the non-convex trajectory optimization problem. So what we query here to the model is like boundary conditions or performance criteria. And then like you have inference model that is trained that returns an initial guess trajectory, which comprises of like a sequence of like states, control, and then states, control, states, control. This is fed as an initial guess of non-convex optimization that we start linearization as a reference. And then hopefully we can get optimal trajectory. And note that SCP is like very much a local refinement that guarantees the constraint satisfaction, but it does not really guarantee the global optimization, if that makes sense. That is like the price we are paying for. And there are many ways to warm start these constraint trajectory optimization, or this history is like actually quite long, for like actually 20 years. And then some robotics people are saying this as like memory of motion. But now recently it's kind of rebranded as a warm starting, and then like some works including diffusion policy or transformer or whatever fancy policy you can think of, and then like throw in to just initialize. Because the great part of this is like you don't necessarily, or you are not directly injecting the control policy to your spacecraft. And then like what you're actually injecting is like a solution of like a constraint optimization problem that theoretically guarantees your constraint satisfaction. So in that sense, we can define whatever safety constraints that we want to enforce. And then by using the output of like transformer as an initial guess, we can like land onto the like nice feasible solution. But we don't want to use AI, as we mentioned. So I would like to compare some like arguments of like why not AI and why AI in space. One of the big argument is like I would say the biggest like differentiation that we have from robotics community, or mainly like like RL robotics or transformer robotics people, are the fact like we have a very good dynamics model, and thanks to like a guidance problem that we developed over the past decade using like EI separation or relative orbital element space, we can get still like extremely powerful analytical solution, closed form solution, or numerical optimization that is like guaranteed to have like global optimality. And compared to, for example, you have autonomous driving, sometimes like people jump into the road and you still need to avoid it type of situation. Currently, the problem we need to deal with is still like not in this level of like like agile maneuvering or like agile replanning or something. And also one of the big questions is like safety. AI fails too often in terms of like spacecraft. Even though like 99% of success rate is like confirmed, it's still not good for space, and then like you don't want to load like that to your like Crew Dragon or something where 5 people are on, and then we develop like like a few hundred millions to like build a spaceship. Another big issue is like a compute. Spacecraft graded compute is like very little, very poor yet. We started loading GPUs, and the CPU is like still very like weak compared to terrestrial robotics applications. That's like a huge like kind of pushback for us trying to load AI on spacecraft. But there are a couple like big advantage we can potentially leverage using AI. One is like people say compute is like a limitation, but if we leverage the offline training and then potentially like online tuning, and then what we need to do is online inference, then the inference cost might be still pretty small to the point we might be able to load on the spacecraft. So that is like one argument people are talking about. And another huge advantage that we can leverage by using AI is like using offline training, we can potentially explore the global solution landscape. And optimality is like very important for a spacecraft because we want to like shave off some like fuel cost. So like being able to use the transformer or inference model as like a motion optimal, like memory of optimal motions, then like we can leverage transformer to generate almost optimal but infeasible trajectory, and then like refine locally using SCP. So that's like combo is like quite reasonable in terms of like practical deployment in the spacecraft. So I would like to go a little bit quickly because I think I don't have much time left. But the workflow of ART is like split into like 2 parts. One is like training and one is like deployment. And first thing we need to do is like a tokenization and then define state representation, essentially how we can feed into neural network, or here particularly transformer, so that like they can learn something or they can understand the context of like what we are doing. And then we train those model by feeding a lot of like trajectories, and then we can deploy this in space. The way we deploy it is like we have like a boundary condition, for example, or your latest state estimate. And then also like desired objective, for example, we want to get there within like 3 hours, or like we want to get there within like maybe like like less than 5 meters per sec of like delta V. And then again, this returns like initial trajectory that we can start or warm start your SCP. So I would like to go into a little bit more mechanics of like ART. How many of you have are familiar with like how transformer generates like, let's say, tokens, or like like open your ChatGPT and then like generate like a war sequence of wars? I guess some of you. Okay, let's just start. Let's say I put ChatGPT, what is a good word? Okay, and then they start like auto-regressively generate the word. What is called? What this means is like like the first output of the transformer is like input, what is a good word, and then we. And then like it automatically refeed into the same model, and then they add one more word. And then as we keep going this loop, keep going this loop, and then we get this. And then that is like something like we have like instantly, like outside as an output of like a ChatGPT. We can use the same philosophy to the we can use same philosophy to generate the trajectory, where you start from like initial state and then go to like output. We can expect the transformer generates the next control, and also like by using control where it's going to go. So next state. If you're familiar with like Markov decision process, this is like kind of very similar to your action in the next state. And then by keep doing this, we can like autoregressively generate the entire trajectory, which is like indeed a sequence of like a state and control. And this is slightly different from the philosophy of like a reinforcement learning. And this is like, there's two critical difference that we have. One is we are actively querying something to the model, while reinforcement learning fundamentally maximize your average return of your objective. And this is like quite different in a sense, like even though we can always like aggressively ask transformer to get the global optimal solution, we can also like able to like query something suboptimal or something like like that is different like scale, if that makes sense. And that is like pretty important for example multi-objective querying or like something like that. Another thing is like it reads entire history and then like the new trajectories are made. This is called sequence modeling rather than like Markov decision process. And it is like these contrasts is like a quite hot topic in versus reinforcement learning. But turns out recently people are discussing that having the entire trajectory context facilitates transformer to learn the underlying dynamics. It kind of makes sense because like they don't know what the dynamics is like underlying like for these trajectories, and then also helps like like providing a good control history, even though theoretically speaking, optimal control provides basically like a sort of like best scenario would be like attainable because of like the Bellman's optimality principle. Anyways, so in order to query a good trajectory, we need to add something. It's called performance parameter, and then this is like an important part that we like add from this trajectory generation scheme like that we can think of in general. This is sort of like corresponds to reward function in the reinforcement learning context, and it's basically comprised of like two things currently, which is like reward to go. For example, if you're here, how much of reward you want to spend to get to the terminal state. And then another thing is like a constraint to go. You can see as like you can see constraint almost formally as like and you can plug the constraint into the objective function as like indicator function and then like its summation. And by doing so, we can essentially treat this constraint violation as like sort of like reward function as well, where you can see where if the state X and U are within the admissible set, we'll give, sorry, this is 0, this is flipped. If these are outside of the set, we give like 1. And then like otherwise, which means like, like if it's feasible, we just return 0. And obviously we want to have this constraint to go to be 0 throughout the time because like we don't want to have a constraint violation. And after we define this tokenization, we solve a batch of like optimal control problem, OCP, and then get like a lot of like trajectory data, which comprises of like this tokenization scheme. Your reward or constraint to go, and then state control, and then repeat. And then after that, we can like just like fit the transformer to have like, essentially this is like mean least square, and we can just train until like it converges. And then when it comes to deployment, what we have is essentially we throw the inputs, for example, boundary condition, or like, okay, or constraint to go needs to be 0 because like we want to have a feasible solution. That is like two equivalent thing. And we keep doing an auto-regressive inference until like the trajectory is generated, and then we solve it as a SCP. Okay, one thing we can leverage is like, like we know a good onboard guidance dynamics. For example, state transition matrix is available in analytical form for relative orbital elements. Therefore, when we actually deploy this, we can think of like a scenario or what we call dynamics in a loop inference, where even though during the training, transformer is required to return both like control and next state, we can simply use only like output control and then propagate using onboard dynamics and then like get a dynamically feasible solution, at least on the onboard guidance level. So which ensures some like sort of like sophistication of like what you can return when you're running ART. So I would like to show some demo. I I'm applying this case scenario for the low Earth orbit, a rendezvous scenario. What you're seeing here as a trajectory is like a quite different from what you saw in like a 279D sequence. But this is like thinking of some like a crude spacecraft rendezvous scenario that needs to happen in 2 hours, so which is quite short time period, less than 2 orbits. And then like what you want to have is like, like to dock some like one of like the docking ports I showed in like a red dot here. And what you can have as a constraint is like, again, passive safety constraint, where you can define some like ellipsoid around like your target or chief spacecraft, which locates at the 0, 0, 0 in the RTN frame. And let's say like you have like a 300 meters of like a keep out zone, and then like your spacecraft is always outside of the keep out zone, not only for the controlled segment, but also uncontrolled segment for a like certain time period. So like as you stop having a control, they start drifting, but at each time step that you're adding control, you want to make sure this passive safety where a drift trajectory is also excluded from the keep out zone. So you can see like this is like a huge number of constraints that we need to think of, and also like it's pretty difficult problem, difficult constraint that we need to deal with. And also, obviously, this is non-convex. And what is art enabling is demonstrated here, where, for example, you're here, and then like you want to get the top, and then these like red part is like sort of what is called keep out zone. And once you solve this like convex optimization problem for this problem, you get something like black dot trajectory, which has a cost of like 4.79 meters per sec, which is okay, sure. Note that this is like a relaxed version of the original problem. So like it should return the lower bound of the objective value that we want to ultimately solve. That includes passive safety. Okay, and then by using that solution as an initial guess, you land on the solution where this is like shown in blue trajectory, which has like a quite higher cost, which seems too similar, but in fact this actually has a displacement in the like R end plane, thus like adding additional delta V of like 5.3 meters. Fine. What if we use ART? So ART starts generating completely different trajectory as shown in the like orange dot, where they return the delta V of like 4.79. Actually, this is below the global minimum or a lower bound of the solution. Why this is possible is like they are not, they're cheating in a sense, like they are not satisfying the boundary condition. We keep just forward generating the trajectory, so there's no possibility that like it can go exact satisfaction of like the terminal constraint. However, if you start this as like initial guess, you can land on the red trajectory, which is like having a almost same optimal objective to the like compared to the lower bound of the entire problem, which is like a solution of convex programming. And you can see that ART can generate a completely new initial guess by globally inspecting a solution. And by the way, the green trajectory and then gray trajectories are all drift trajectories. So like you can see they are like, technically there's like two keep out zone I'm defining across the phase, and then gray trajectories are always outside of like the blue trajectories, blue ellipse, which is I call approach ellipsoid, and then also green trajectories when you're closer or a later phase, they're always outside of like the keep out zone, which is like a red ellipse. So passive safety is achieved. Perfect. And the question is like, okay, there's like a huge pipeline. Can we actually benefit from it? And then like we did some like statistical analysis for it, and there are a couple of statistical metrics we introduced here, including infeasibility rate. So once we solve the SCP, can we actually get the higher feasibility or higher like like trajectory generation rate in general? Also like can we gain some optimality in objective, or can we actually accelerating the compute by reducing the iteration of SCP, because we are hopefully starting your initial guess close to your basin. And then all like infeasibility rate and then optimality improvement and then total runtime, you all see like the orange bars are lower than blue bar, which means like it's better than like the solution that is like initialized from the convex optimization that just as I show in the like a demo slide. So in general, like we are confirming some like statistical improvement by leveraging AI-based trajectory generation scheme. And this is like a collaboration with like ASL, but we are also deploying this in the hardware using FreeFlyer. And you can see that the blue trajectory that is like generated based on art is completely different from the blue trajectory that is like basically generated based on the more like heuristic way. And we also validated this in the hardware. So conclusion, original motivation was like to fuse the learning-based method and the optimization-based method to realize some like global search of trajectory while ensuring the like rigorous constraint satisfaction. And the proposed architecture art is like high performing initializer of the non-convex optimization. And then that's like one way we're trying to push as like a potential paradigm of like AI application in guidance and control. Obviously, this is not the end of research. There are many things that needs to be done towards like proof of concept that we have to actual onboard deployment, including runtime monitoring, hardware testing, including like edge computing devices to like actually mimic the spacecraft grade compute. And also like generalizability is like a huge problem. If we want to change a scenario, can we have like art Leo, art Geo, art Sister, or can we actually get more like a foundation model approach where everything is like generalized? I mean, that's the utopia world. We'll see how it goes in the next like couple months. And also, great advantage of using transformer is like it has a very good affinity to the multimodal input. For example, if you have like image that Pulse provided, and then like can we actually add any information or context to that by using transformer is like one big question we have. Maybe yes, maybe no. We'll see how it goes. And last of all, this is like a research project going on with Blue Origin and also like under the name of Caesar, collaboration with like SLAB and ASL. And these are all people who are working on art, and I'm just like kind of promoting this. So yeah, thank you so much. I appreciate it.
Thank you. Very well done in just half an hour.
Yeah. Yeah, I'm here. So if you have any questions, like feel free.
So I have office hours today, so if you have questions about the final project and this final leg of the course, please see me. And otherwise, good luck with the finalization.